Greetings, Kerbonauts! This is Scribble Space Program. I'm Bob Fitch, and this is episode number 14 of Project Ares. And now, I used to say it was the real solar system look at an alternate Earth history, but it's a combination series now. We're playing with Galileo's planet pack, and we will get back to some real solar system work as well. At that point, I'll probably be looking at playing in both worlds simultaneously. For now, I'm going to do some catching up with just Galileo's planet pack, though. Anyway, when we left off last episode, we were looking at this launch right here. I didn't say what it was for, but this was going to be our first attempt to take a look at the nearby moon, the closer moon that should be Mun, but isn't. The Kerbals were discussing what was going on, where they were, and why they were seeing weird things in the heavens, and they looked up and somebody said, "Do you have any idea what that is right there? That doesn't look like our normal moon." And another Kerbal said, "I don't have one iota of an idea what that is." And so they've started calling that one Iota. And then somebody else was looking up and saw Minmus, but it wasn't really Minmus, and so they said, "Hey, what's that place over there? Doesn't look like Minmus." Another Kerbal went, "I don't think it is. We should give that one a different name." And then another Kerbal says, "Can we call that SETI Alpha 5? That would be so cool." But everybody else argued with him and said, "That doesn't make any sense. We don't have SETI Alphas 1 through 4. Why would we call that one 5? Let's just call it SETI." And so the new moons are Iota and SETI. So getting back to the launch we're looking at, it is having some problems. At the beginning, when trying to make my gravity turn, the little fins on the bottom made it very difficult to turn, actually. You could see me early on as I was fighting the controls. I was trying to push the nose down, and the aerodynamics were trying to push it back up again. So that was hard to get going. Once we got a little higher, it was easier. But once we got higher and had to decouple, the whole thing did a little flip again, just like in a previous launch I had. But we get it righted, going in the correct direction, and activate the cool engine that has the big nozzle that sort of extends down after it has been activated. That's pretty neat. But there is something going on with the engines. I had said last episode that I didn't think I was getting the right amount of thrust, and I still haven't figured out what that problem is. I believe that my thrust should be higher than what my thrust to weight is when it shows up in the real game. I did some tests and I created an extra window. You can see this new one I've got here under my flight computer. It says performance. And so I put in some stats in there to try and track what was going on. And one thing I noticed, one thing I didn't notice was while I was playing around with all of my windows and trying to get them set up, I didn't look at my altitude and I started to drop. I didn't completely give up right away. I tried to fight it back up into an orbit, but little did I know it was already too late. Anyway, I was saying one thing I noticed about the engines, was the drag losses are much higher than I expect them to be. I expect about 200 meters per second by the time I get to orbit on the drag losses, but I'm getting 400, 500, 600 meters per second of loss. So I was thinking that maybe what was happening was something's up with the environmental, the aerodynamics, the drag, perhaps the fairing is not actually covering up things like it's supposed to, but this is a procedural fairing, so it is supposed to be covering up the payload and not creating extra drag. You know that I have that mod called Old School Fairings. Well, I haven't been able to get that to work in the latest version of 1.2. I tried all kinds of things that I could think of, and it just doesn't seem to be making the drag go to zero like it should for the payload when I have that mod installed. So I don't have that. I'm using the procedural fairings, sadly. So this thrust/engine problem is probably not that, but the drag is coming from somewhere, and I don't know where, and I'm not even sure that that's exactly what the problem is. I just know that I'm spending way more than I should on these launches. Speaking of which, in the last episode, I told you that I was going to do all the math by hand to figure out exactly what it was going to take to do launches and to make it to these other planets. Like, we're going to Iota right now. That's the closer moon. I haven't shown you what that math is. I'm going to do that real quick for you here. All right, we're going to need to know some altitudes of the different places where we are and where we want to be. We're going to start off on the ground, so let's just say start of 0. We want to end up in orbit. Now, just to test this out, I'm going to put in here, let's say we want an ending altitude of 100 kilometers. And so to get the radius from the center, we're going to add 600 kilometers to whatever that altitude was, and that will get us that. Now, for the semi-major axis, we're just going to average the two of those values together. We also need to know the gravitational constant, the g times m, the mass of the planet. We figured that out last time with our experiments. It's 3.53 e to the 12. And now with that, we should be able to get the velocities that we want to go. I've talked about this in the past before as well. You just take the square root and you multiply that times the gm, and then that gets multiplied by 2 over whatever the radius is minus 1 over the semi-major axis. And that is going to get us one of the velocities that we would need to be for an orbit like this. So let's say we wanted to orbit. I know there's atmosphere and you couldn't really do this, but pretend you could. Suppose that you were in an orbit going from the surface up to 100 kilometers. Well, at your, let's move that up 1 to the semi-major axis. If you were in an orbit like that, you would be traveling at your periapsis 2517 meters per second and at your apoapsis 2158 meters per second. Okay, so that's going to help us get how much delta V we need in order to get off of the ground. For starters, we would need to spend this 2517, but it's more than that. We're going to have to spend for atmospheric drag as well as gravity drag, but it will also be a little bit less because we can account for the rotation of the planet. We have determined that we are at the equator. So the radius is 600 kilometers and the day length is 21,600 seconds. So the speed that we are traveling at the equator, first we need to find out what's the circumference around the equator. So that's 2 pi r, if you remember your math there. So 2 times pi times the radius, and then we'll divide by the number of seconds we're doing that rotation. So we're traveling at 175 meters per second. So let's go over here and start another column of things. Let's go with how fast do we want to be traveling? We want to be traveling that. How fast are we starting out? We are starting out going that fast. So how fast do we need to increase? How much do we need to increase? Well, we'll take the top one, subtract the bottom one, and we need to add 2,300 meters per second to get going. But there is atmospheric drag. It's typically supposed to be about 200, and I still have to figure out why it isn't 200. Something's going wrong, but I haven't figured out what it is. We also need to calculate the gravity drag. That'll probably come out to around 900. I'll explain how I know that in a minute. Then we have our subtotal, or actually that's really our total, isn't it? If we add those three together, now we know that that's about how much it's going to take to get a typical craft off the ground without just going really too fast or anything like that. If we go too fast, this will go down, but this will go up. So it's really just a balancing act between those values. We also don't want to burn up by going too fast. Anyway, how did I know it was about 900? Well, if we go and we set another section up here, let's say that we know that gravity is 9.8065 meters per second at the surface. And for about the first 30 seconds, we're going to be going straight up. And so the angle for that is 1, just straight up in the air. So then we can figure out what all this is. We'll just multiply this times this times this. And for the first 30 seconds, we're going to lose about 300 meters per second to gravity. Once we get a little bit higher, then the gravity is going to go down, and we're going to be angling more at sort of like a 45 degrees, although eventually we'll be going 0. So we'll split the difference and we'll say that it's around 45 degrees for the next few seconds. In fact, how long? Let's say that we're going to go for about 90 more seconds at an angle of 45 degrees. Well, in order to get that, we need the cosine of the radians of 45 degrees, and that'll get us 0.71. But what is the gravity value we should put here? Well, it's going to be somewhere less than this, but not like 1 or anything. We need to take a guess at what that is. So let's say that we don't know what it is. That's what the x is. We don't know what the gravity will be for a good portion of the flight, but we do know that it's 9.8065 when we're down at the surface. Now, suppose after a little while we're somewhere around, let's say, 30 kilometers in the air. Well, if we take the square of this and the square of this, that creates a ratio that we can use in order to figure out what the gravity would be at 30 kilometers. And it is going to be this divided by this times that. So only 8.89 meters per second once we get some altitude. I don't know what it's going to be. I'm just going to put a 9 here, and then we'll multiply all those together and we get that. And if we make a total where we add these two together, then you can see it's about 867. Well, I'm just going to fudge it up and say 900 meters per second. And that's where I came up with this 3443. But that's just to get us into a 100-kilometer orbit. What we actually did was we fired some lasers at that moon we're targeting, and we checked to see how long it took for the lasers to bounce back to us, and that gave us the distance to the moon. And so now we know that it is actually 27,400,000 meters away. And so that changes the velocity that we need when we're leaving. Now, technically, it doesn't need to be this high, because that would only be true for going up to something that has no gravity, if we just wanted to get to that altitude. If we're going up to meet something that has gravity of its own, this is going to change, because once we get closer, the gravity of that thing is going to pull us and add some velocity to us. But if we have at least this much, then we should be really safe. So if we figure all the rest of it is going to be somewhat similar, then we know that we need about 4,300 meters per second in order to at least reach our target. Once we get there, we can do a gravity experiment to figure out what the density of that planet is, and then we'll know what we need in order to make a stable orbit. So for this first flight, we are just trying to get close enough that we can do that gravity experiment. And with the moon Iota just coming up over the horizon, it is time to launch again. You've already seen this once, so I'm going to skip ahead to where something interesting happens. Right here, once again, you can see that it was still hard to move because it's so small and the fins are down there on the bottom, giving me the control that I need in order to move it, but also it's forcing it to go as straight as possible. No matter how far I go off of my attack vector, it pushes it right back to the middle again. So that's why it jiggles a lot. It still has that high drag. We haven't looked into why that's happening yet. One thing I did differently was after the first stage burned out, I let it go for much longer before I decoupled that so that it wouldn't flip over. That worked, and so when it decouples, that just glides away. We don't have to worry about that. Power up that lower engine, well, the second stage engine, and get rid of the fairing. That's when I see that we still have a little issue with the fairing decoupling. It bumps into the launcher. No damage this time, but it could have been a problem. We should increase the strength of the fairing for the next time. Make that pop off a little harder so that it gets further away from the craft before we fly into it. And then that's it. We just go like this until that second stage completely burns out. There's more fuel on the satellite itself, so once we burn it out and we're still kind of in a low orbit, then we can decouple and just get the satellite going in the right direction there. And then we'll see what's the next problem we're going to bump into, and it has to do with the solar panels. I use my action group number 1 to extend them, and when I do that, nothing happens with them. I mean, they're open, but notice that they're not tracking the sun or anything. If I rotate the craft around, point it away from the sun, toward the sun, nothing is happening. Take a look at this right here. It shows that there's 0 sun hitting the panels. So something must be busted. I opened up the console, looked at the debug log. I saw this message in there. So that explains what's happening, but it doesn't tell me why that's happening. Maybe it's the particular solar panels. I'll need to do some investigation into that. Anyway, I've got my communications antenna opened up now, and we're just going to wait until we get around to our descending node so that we can make our burn to head over toward Iota, because as it turns out, I'm either not on the equator like I thought I was, so we're going to have to double check on that, or when we launched, we went into a very terrible inclination relative to what I really wanted to do, which is to go east and head straight for Iota. No worries though, we have enough delta V, I think, so I set up a maneuver node that will just raise the destination up a bit, meet the orbit of Iota, and then we can get underway. I had to move further ahead on my orbit than I had really wanted to in order to get to that descending node, which is why we're going up above the orbit and then slowly dropping back down as Iota comes in. On the plus side though, it does mean that it makes it fairly easy to come in over the pole, which is what we were going to want to do anyway to get a good look at the planet. Now in this part where we're fast forwarding, I was concerned that my battery would drop down because if the solar panels actually aren't working, that I might run out of power, but it looked like it was barely changing at all. So either they are working or the battery's not dropping when it should have, and there's yet another problem I'm going to look into. Once we entered Iota's sphere of influence, I activated the gravity meter, but it said too far away in order to make a measurement, so we're going to try and get closer. And that's when I bump into another wonderful little discovery. If I tell it to warp to a location, which I've never actually done before, I've always used the automatic warping and slowdown that came with the Kerbal alarm clock. But when I tell it to warp ahead, and then I think to myself, oh, that's not going fast enough, and I hit warp faster, it actually disables the warp point, and I zipped right on through. Oh dear, hopefully we do have enough delta V to get our reading from this far away by slowing down. We're gonna find out now. Sure enough, I did. In fact, I still have about 300 meters per second left. That should be plenty to bring that periapsis back up so that we don't crash. And then once we get around to the periapsis, bring down the apoapsis and even circularize at a relatively low altitude. I'll probably target something like 40 to 60, maybe around 50 kilometers altitude. Now that we're closer in a relatively nice orbit actually, we're going to go around several times taking various measurements. We're going to analyze the surface from up here. We're going to check for the gravity, get a reading on what the pull is there, the meters per second downward pull from this altitude, which we can use in order to calculate the mass of the moon. We'll also analyze the radiation to see if it's going to be dangerous to the Kerbals and do some other environmental analyses while we're up here. We've got these little ion traps and various instruments all around on the satellite. Send that data back over to Gale and then do the mass calculation that we've been dying to get to. Okay, so now with that information, remember last episode I said that the force of gravity on something is big G, the gravitational constant, times the one of the masses, times the other mass, and all divided by the radius squared, where the distance between those two objects. And we also learned that last time the mg, the force, is just the mass times the gravity that's being applied to something. And since m was on both sides, we were able to cancel out one of those m's on each side, which leaves us with this. And so now if we just multiply both sides by r squared and divide both sides by g, we're going to get g times r squared, and all of that would be over over g, the gravitational constant, and that will be equal to m. So now we can get the mass of Iota. We just need these values. We need g, the big G, the radius, and then we can calculate the m. So the g, we just measured it. It was 0.32 meters per second at a radius of about 61 kilometers, and we've already measured the object itself is 100 kilometers, so that is going to be equal to 161 kilometers from the center, and put the zeros on there, and that needs to be squared. The big G was 6.67, e to the minus 11. And that's it. Now we can just do the math. So that was the g times the r squared divided by gravitational constant gets us a number of kilograms equal to 1.24 e to the 20. And with that, now we can do all of the math we need. We know what it takes to get off of our new planet Gale and how much it takes to get to Iota. And with this, we'll be able to tell what it takes to capture an orbit, as well as to land and lift off and come home again. And that will be our next objective.
And that's over the entire planet? Yes, sir. All the scans show the same thing. There is no life on this planet other than us and any animals that came through the dimensional barrier within 1 kilometer of the base. It's as if a 1 kilometer radius bubble of matter was just transplanted and dropped onto this world. We're lucky we didn't come in further out in the ocean, or we might have sunk.
What's this?
What did you find, Gail?
Are you seeing the same reading from 113 by 67?
Checking. Yes, a signal. Food storage rebuilt and some hydroponics created near the... Yes, Gail?
We've picked up an artificial signal in the skies.
One of our satellites?
How can it be? We don't have anything in these skies to be detecting.
Oh, right. Well, what is it then?
If I were to guess, I'd say a distress beacon.
And that's going to do it for now. Next time we'll go to the moon of SETI to do the same scans we did on Iota. And we need to start messing around with the life support and manned flights. We'll investigate that strange signal we're getting that Gail Kerman says might be a distress beacon. This flight for SETI is a new launcher because I figured out that Ven's stock revamp, that mod was causing the solar panel problem I had, maybe even the engine problem. It's not updated for 1.2 yet, so I had to remove that mod, and that caused my install to lose all its craft files because the parts from there disappeared. So we can look at this launcher and its new scanning satellite payload next time. Until then, I will see you later, Kerbonauts.